before, that the Hartree-Fock is a theory in which you have only, everything depends only on the one particle. So, what is it? Well, it's the gamma acting on -1/2 Laplacian minus Ex, because these are the one electron terms. So each electron just comes in with a gamma. Then there is the electron-electron repulsion, and that's a bit complicated. There are two terms when you go through the calculation. There is what's called the direct term, which is the density interacting with itself through the Coulomb potential. But this would not be quite right, because I would be overcounting. Here, electrons would be interacting with themselves. And if you do the calculation carefully, you actually find that there is a correction term to that, which comes from that too. Now, this is not a difficult calculation, so I will leave it to you if you haven't seen it before. But there is this additional exchange term. But everything depends only on the gamma. Let me, however, describe something called the Lieb's variational principle, which makes Hartree-Fock theory a little easier to work with, because I want to define, just as it did in the quantum case, the Hartree-Fock energy by minimizing over all the gammas. And remember, gamma was a projection onto the span of the phi 1 up to the phi 1. So I would minimize this over all projections of dimension n. Well, the dimension of the projection I could just write as trace gamma. But I claim that I get the same if I instead take the infimum over everything that just satisfies the Pauli principle. 0 gamma, 0 less than or equal to gamma less than or equal to 1. I relax the minimization, not just to look at projections, but to look at everything which is just between 0 and 1. The point is that this functional, this Hartree-Fock functional that we have there, makes perfect sense as long as gamma is just an object, a trace class operator between 0 and 1 with the trace field. So let me just prove that it's correct that these two are the same, that this relaxation did not change the energy, and the proof I gave here follows Bach. I mean, this is the proof of this and this identity here. This was the definition. So first of all, it's clear that I get something less than or equal to, because I'm relaxing the minimization. I'm minimizing over a larger class, so this number is clearly less than or equal to that number. So what I want to prove is this inequality here, that I'm actually getting, that it's also greater than. Now again, I will not do all the details, so let me first say that we can, when we do this minimization, we can restrict to say we minimize only over things that have finite rank, not rank n, but just finite rank. And I then write this one-particle density matrix like this. In its spectral decomposition, it has finite rank. So I 1 to m, lambda I, finite rank. Now the lambda I is between 0 and 1, and they sum up to m. So if they're not projections, then not all of these lambda i's would be 1. Or 1 or 0. Okay, but let me notice that when I calculate this term here, the rho gamma x, rho gamma y, minus this gamma x, sigma gamma y tau, this was exactly the terms that appeared here and there. I'm combining these two terms. So I'm looking at this expression. This is actually what's called the two-particle density matrix. Then, if I calculate this for that gamma here, then, as I will explain down here, I can write it as a sum over lambda I, lambda j, for I different from j, or here I'm just saying I'm summing over all pairs, with some positive or non-negative coefficient. Notice that there is no lambda I squared or lambda j squared. And let me just try to explain why. I mean, when you start calculating So from here, you will get the phi I x squared summed on I, phi j y squared summed on I. But here I wrote it in a symmetric form, so I have phi I x sigma phi j y. So I wrote the symmetric form, that's why I'm summing over each pair once. And then this exchange term, the thing that comes from lambda I lambda j, well, there will be a term which is phi I x sigma phi I y tau. That's the gamma coming from there, from the x sigma y tau, and then multiplied by the complex conjugate, sum over I and j again. And there's the symmetry on each. But then you see by simple Schwarz inequality that this thing here is actually greater than. So, in fact, this term is lambda I lambda j with positive coefficients. And if I go back and look at the way the Hartree-Fock energy was calculated, this term, this function is multiplied by x minus y. I mean, when I say that these coefficients are greater than or equal to 0, they depend on x and y. But they're divided by x minus y and integrate. So, in other words, if I think of the Hartree-Fock energy now, and remember that gamma is not a projection. I'm assuming gamma not being a projection. But the lambda sum up to n, to an integer. That means that there must be at least two coefficients that are not 0 or 1. They sum up to an integer and they're between 0 and 1. Right? But they're not all 0 and 1. So there must be at least two that are not between 0 and 1. And I want to argue that I can do better for the energy, or at least as well for the energy, by either removing 1 to 0 or the other one. So I change lambda to lambda 1 plus delta, and, oh sorry, this should have been lambda 2, I'm sorry. So it should be lambda 1 plus delta, lambda 2 minus delta, and now I want to see how the energy depends on delta. But you notice that all the terms here and all the terms there, most of them will just be either independent of lambda 1 and lambda 2, or there will be a linear term in lambda 1 and lambda 2. So there will be a constant that does not depend on delta. There will be a linear term in delta. And then there will be a term that comes from the term lambda 1, lambda 2, which is lambda 1 minus delta, lambda 2 plus delta. So this will be a minus delta squared times positive coefficient. And then I integrate it divided by x minus y. So all in all, I will have this expression here with a being strictly positive. And therefore, this is a concave function, and it's best to make delta either as small as you can or as large. Right? The restrictions for making delta large or delta small is that you might make this 0 or 1, but that's exactly what we want to show, that we make 1 or 0 or 1. So that's Bach's proof of Lieb's variation principle. So that actually leads me to the next model, what I call the reduced Hartree-Fock model. And that's the one where I remove this difficult exchange term here. And say, let me try to ignore this. Let me make a model that has only the first term, only the direct term. That's clearly not the best I can do, and I'll discuss later on what the difference means. But it's a much, much simpler function, because now it's a convex function of gamma. See, this here is linear in gamma, and rho gamma itself is also linear in gamma. So this is, remember that the kernel x minus y is a positive kernel. So this thing here becomes actually a convex function of gamma. I'm not saying it's strictly convex, but it's a convex function, which is much simpler than Hartree-Fock. The Hartree-Fock energy, because of that term, is not a convex function. And in fact, we do not know in general that the minimizer is unique for Hartree-Fock. We do not even know that the minimizer for the Hartree-Fock is spherically symmetric. I haven't discussed minimizers yet, but I'll come to it in a moment. But we have, it will not in general have a spherically symmetric density. The minimizer for quantum mechanics will also not in general have a spherically symmetric density. This is well known, atoms can have angular momentum, but nevertheless, we very often think of angular momentum and spherical symmetry, but it's not entirely correct to talk about these quantities when we have. But it's not quite correct to talk about orbitals having angular momentum. Atoms have total angular momentum, but they are not spherical, and it's not quite clear that we can attribute good quantum numbers to angular momentum orbitals. But this is something I will get to later on. For the reduced Hartree-Fock, where we remove the exchange term, then the density will actually be spherically symmetric because of the convexity of this function. And again, just as I did with all the other models, I define EZRHF, the energy with n electrons, to be the infimum over now 0 between gamma and 1, and then this functional that I wrote there with the condition trace gamma to n. But now there's no longer any reason for n to be an integer. N can be any positive, non-negative values. In fact, for Hartree-Fock, because of the deep variational principle, you could also define this even if n is not an integer. Here, n needs to be an integer, but over there, you could actually interpolate between the two. It's not quite clear that this is so meaningful for non-integer n for Hartree-Fock. For the reduced Hartree-Fock, it's a very nice interpolation because it will actually be a convex function of n. So this energy here would be a convex function. So let me go through these properties that I had for the quantum, right? I talked about whether it was a decreasing function and so on. Let me do these properties 1 to 4. Let me go through these for the Hartree-Fock and reduced Hartree-Fock model. So I'm using sharp here to either refer to rough Hartree-Fock. So sharp means HF or reduced Hartree-Fock. Again, these are non-increasing. This is a non-increasing function. For reduced Hartree-Fock, it was also convex. Minimizers exist for n less than or equal to z. This time it was proved for Hartree-Fock by Liebensteiner. For reduced Hartree-Fock, I proved it, but it's not particularly difficult. Minimizers do not exist if n is too big, and if you remember, we had this n less than 2z plus 1. That is that they did not exist if n was greater than or equal to 2z plus 1. This was Lieb's theorem. But this also holds both for a reduced Hartree-Fock and for Hartree-Fock, but one can prove, at least for large c, something slightly stronger, that it actually already, the 2 here is not really the optimal thing, and you can actually prove that you do not have minimizers if the z n is bigger than c plus a constant in both Hartree-Fock and reduced Hartree-Fock. But I will get to that. I'll get to that later. And again, you can define the ionization and the radius as for the quantum model. So if we can maybe say something in one model, or maybe one model is too difficult, we will try to say something in another. And let me just, I'm coming to the end, but let me do the comparison between these atomic models. The Hartree-Fock was a relaxation of Hartree-Fock was a restriction, of the minimization of quantum. In quantum, we minimize over all wave functions. In Hartree-Fock, we minimize over Slater determinants. So therefore, the Hartree-Fock energy is bigger than or equal to the quantum energy. The reduced Hartree-Fock, we remove a negative term, the exchange term, so we get something bigger. And because of that, we have already seen that in Hartree-Fock, we can relax minimization, that we do not have to look at Slater determinants, but only on one particle density matrices between 0 and 1, then we have an inequality there. So the first inequality follows because it's a restricted minimization, and the second is Lieb's variation principle, and because the exchange term only goes. And as I said, the minimizer here is very asymmetric because it's actually the density is unique. I'm not saying that the gamma is unique. It's strictly convex in the density and it's convex in gamma. But for quantum and Hartree Fock, the atom is not necessarily so. Let me take a few more minutes. I wanted to both introduce the variation equation for reduced Hartree Fock and then just mention Thomas Fermi theory, which is the model I want to discuss in the next lecture. But if gamma is a minimizer, with trace gamma equal to 1, then there is, so I'm trying to write down what is the variation equation. I claim there's a mu greater than or equal to 0, so that gamma minimizes the trace of what I call the mean field operator. The mean field operator is -1/2 Laplacian minus z over x, plus what an electron would feel from all the other electrons. So rho star x inverse is the electrostatic potential created by a density rho. So this is the attraction to the nucleus and the repulsion from all the other electrons. Actually, not all the others, also the electron itself, because here I'm counting cell interaction. What I'm saying is that if gamma is a minimizer for this, then gamma also minimizes, is a self-consistent gamma that minimizes this expression, meaning that it actually gives you the sum of the negative eigenvalues of the mean field operator when you add a plus mu to it. And the proof is not difficult. I mean, you just use the fact that this is convex, and that means that you can find the mu so that you can, I should here have added, sorry, I should have added plus mu trace of gamma. I should have added this as a Lagrange multiplier, if you want. So because it's convex, I can sort of, the restriction that I have on n, I can replace it by adding a mu and saying, then I minimize the whole thing. But, and this I should also have done down here. I should have said plus mu trace of, sorry, I've forgotten that. But then I use the fact that if I have another gamma, a gamma prime, then if you want, because of all the mistakes I made, forget the mu, think of the mu being 0, then you want to say that if you look at the combination 1 minus alpha gamma plus alpha gamma prime, this is a new one-particle density matrix, and you must have the minimum when alpha is equal to 0. So when I take the derivative of this thing here, at alpha equal to 0, it must be greater than it. There's no problem in calculating these derivatives. These are just really polynomials in alpha. Right? And when you calculate it at alpha equal to 0, you see that it immediately just gives you the trace of the mean field operator of gamma prime minus gamma, particularly if I remember to put in u. So this thing is always greater than or equal to 0, meaning that the trace of this is the smallest it can be, which is the sum of the negative. Well, the time I've already gone past time, so maybe I should introduce the Thomas Fermi model in the lecture this afternoon and discuss it then, and I'll just stop here. So thanks a lot for your attention.
Thank you, Jan-Philipp, for this very nice and clear lecture. Floor is open for questions, comments. Yes, so we have this nice microphone cube, which I will try to throw at you.
Thank you very much for your talk. Can you hear me?
Is it on? Is the cube on?
Thank you for your talk. Can you hear me?
Yes, I can hear you.
Great. Well, you introduced 3 different variational models, and we have 3 different energy for them.
and each time it seemed like you try to make the other model like easier than the previous one. And the question is like, how far are these energies? Like, what are they good approximation of each other, or is it even realistic to consider all these reduction or not? Thank you.
Yeah, thanks a lot. So I will get to that later on. I will tell you exactly. So what I did now was this simple comparison, right? That the quantum is smaller than the Hartree-Fock, which is again smaller than the reduced Hartree. So I will actually in one of the next lectures show a lower bound on that compared to the reduced Hartree-Fock. And this will be an error in terms of when Z is large. So when Z is small, for small atoms, of course it's a little hard to say are they good approximations or are they not good approximations, because for finite Z and a finite N, these are just three different numbers, and then I guess it's a little bit up to what you think is a good approximation or not. We need a parameter that we can vary in order to ask whether it's good or bad. And I want to think of larger atoms and the complex atoms, and I will discuss that they are actually fairly good approximations, and they are better approximations than I can prove here in these lectures. I will prove how good an approximation this is. I can say right away that we saw already that this Z was bounded below by, if you remember, it was Z squared into the 1/3. So if I do the neutral case, I would actually, they're constants here. So this will go like Z to the 7/3. And it turns out that this is the correct energy. So if you do EQZ of Z, this behaves like Z 7/3. I will explain that later on. And in fact, the error that you have in these approximations is little O of Z 5/3. This is very difficult to prove. I'll not get there. I'll try to discuss the little O of Z squared. However, this is not actually such a good approximation, because chemistry happens when you want to try to remove one electron. And the ionization energy, for instance, the one you get by taking a difference between Z and Z minus 1 electrons, is for large Z, presumably of order 1. And I will prove in these two models that it is of order 1. And then, of course, estimating something with something that goes to infinity, Z to the 5/3, is not a good approximation to something of order 1. So these approximations are not good if you want to understand chemical properties. But that's from what we can prove. When you actually look at numerics for small atoms, they're actually not so good.
Any other questions back there? If you can pass it on.
Hello, thank you for your presentation. I have I think a notational question on slide 16.
Yeah.
So what does the minus mean there in the first equation?
Thanks a lot. You mean this minus here?
Yes.
Yes. What I meant by that was that you can think of the function that takes t to t minus, which is simply the function which is 0 here, and then it's negative there. So it's t minus is the minimum of t and 0. But so this is a continuous function of t. And I'm using if you want the spectral theorem, this is going to be a self-adjoint operator. And what I'm doing is I'm saying that I'm taking this operator and evaluating this continuous function. But that's a very complicated way of saying things, and maybe it was an unfair way to write it in such a complicated way, because you will actually see that this is the same as the sum of the negative eigenvalues of this operator HZMF. Sorry, this was RHF. So this is the of this operator RHF Z mean field. Now I haven't discussed why so this function here means that I'm looking only at the negative part of the spectrum. I haven't discussed why the negative part of the spectrum consists of only eigenvalues, but that's a fact. So this trace of the negative part of the operator is really just another way of talking about the sum of the negative eigenvalues. And that's really the bound states for this operator, or the bound states summed below the mu.
Okay, thank you very much.
Any other questions? If not, maybe let me ask one. So going back to this Aufbau principle, right? So you have this way of drawing the periodic table with these blocks for different L's. Why are there always 2 rows before you move to the next L?
I don't know what a good explanation is for this. But,
Okay, but when you say periodicity in particular, you say you assume that it keeps going like this. There's always 2 rows.
yes.
But I think so. Your last statement that this is not actually correct. Does that basically mean it's not actually like that, or?
Yeah, it's not like that.
Yeah.
And also the ordering that you're not counting is not like that. You're not counting the L's in this order of filling up the L's by filling up the lower ones before the higher ones. I don't know what the correct ordering is in any way. I just know that this thing that the thing I put as the thing I sort of put in the box here, I know that this is not correct.
So you will eventually tell us what the right formula is, but deducing from that what the sort of the right periodicity is not clear.
That's not clear, and certainly not what it is, and whether no, I don't know. That's right. That's not it. I'm not claiming none of that. Sorry, I should say that we will get to talk about periodicity. We will talk about what happens and in what sense what I expect to be the right continuations of these columns. And actually, August, who's giving a talk, I think maybe on Friday, he will talk about that. What are the z values that should correspond to the same groups? But we cannot prove that that's true for the quantum model, but we can prove that it's true in one of the simpler models.
Okay, so maybe one last question all the way up there, if we can manage to get the cube there.
Okay, thank you for your lecture. So I'm just wondering if you have a similar variational equation for the Hartree-Fock equation. So you wrote the equation for the review Hartree-Fock equation, but if you have the same equation and with the same property for the Hartree-Fock equation.
Yes, you talk about this variational.
The first equation.
Exactly. Yes, so there is a similar thing there. I didn't want to write it down because it's a bit more complicated, and the thing is that here, for reduced Hartree-Fock, I did not include the exchange term. So, and that's why you have only that part in the mean field Hamiltonian. There is also a mean field Hartree-Fock Hamiltonian. So, maybe I can write it like this. So, if I do Hartree-Fock and I do mean field, then I would have the same thing. I mean, something that corresponds to this guy. But then there would be a correction. There would be sort of an operator, an exchange operator that comes. It's again, but now it's not a potential. That is what it becomes a spin-dependent operator. So it's a bit more complicated. But there is an equation like that.
Thank you.
Okay, thanks again. Jan-Philipp, we will see you again this afternoon.
Yes,
and
looking forward to it.
we will have a coffee break. I hope you will also have a chance to grab a coffee. Thanks again. See you later. See you. We're a bit behind schedule, but I suggest we make about 20 minutes break and we